It's customary to thank the organizers. I would like to distinguish between thanking, in particular, the local organizers for the practical part of this terrific meeting and the scientific committee for the scientific content of the meeting. Of course, the organizers, there are two different kinds, and both of them do their part, so thank you both. Okay, so Cartesian cubical model categories. This is some new work that I've been doing for the last 10 years or so. This interaction between homotopy theory and type theory that goes under homotopy type theory has been very fruitful for providing some mathematical foundations for the theory of type theory, proof assistance, some topics in programming, computerized proof checking, and so on. Most of the utility has been from ideas from homotopy theory and higher category theory flowing into the theory of type theory and proof assistance and so on. This talk is an example of maybe a little bit of backwash, as it were, a kind of reverse flow of ideas from type theory coming back into homotopy theory. And one of the things that happened is that the first model of the univalence axiom of Awodey in the category of simplicial sets using Kahn complexes was not constructive. It was given using whatever it took to get the model to work. But then immediately the question was, can we make this model more constructive? Can we use constructive machinery to build this model? And that quickly led to ideas coming from not simplicial sets, but from cubical sets. Why that's the case is a topic for a lesson here. But, you know, cubical homotopy theory has a long history too. The original work of Kahn was cubical, not simplicial. Jardine, Ronnie Brown, other people have worked on cubical homotopy theory over the years, but it's kind of a curiosity. It's not really the mainstream. But for some reason, this approach proved to be more useful in building a constructive model of homotopy type theory. And that is somehow coming out of the type theoretic side of things. And now there's a kind of interest in cubical homotopy theory from the point of view of building these cubical models. Now, the cubes that we're using, unlike the cubes that, for example, you'll find in Rick Jardine's work, are what I'm going to call Cartesian. They're closed under finite products. And this is actually also an old idea. It goes back to some lectures of Bill Levere, where Bill stressed that you could make a homotopy theory using Cartesian cubes, and you'll have a tiny interval, which is a little bit like in synthetic differential geometry, where you have the tiny ring object there. And so this tiny geometric interval indeed plays a role in our theory as well, and I'll point out where that's the case. Okay, now I've gone a little off script and lost a little time, but let's see if I can recover. So the cube category that I'm using here, which is replacing the category of simplicial sets, is it's simply defined as the opposite of the category of finite, strictly bipointed sets. So it's a Levere theory. It's the Levere theory of an object with 2 points. That's it. It's the free finite product category on a bipointed object. And the presheaf category then on that cube category is what I'm going to call the Cartesian cubical sets. So it's covariant functors from the category of finite bipointed sets into the category of sets. There's a typo already. Look at that. It's B into C, not B into C set. But anyway, there. That should be set. Awodey's law states that when you first look at your slides, you'll discover a typo. There it is. Okay, among all these cubical sets, there's the one cube. It's representing that distinguished functor that forgets those 2 points. So there we are going into C set. We're taking B into C set. And, oh no, it should also be into set. Sorry about that. Okay, so that's the representable there. And it generates the whole category of cubical sets under finite products and then arbitrary colimits, right? So that's a very special object. It has 2 points, of course. The representable points, but it has a special property that those 2 points have a trivial intersection. And in fact, this category, so I'm going to call such an object an interval, a bipointed object such that the 2 points have a trivial intersection. And this category of cubical sets is the classifying topos for such interval objects. You can show that without great difficulty. It has a little bit of topology in there. This interval provides a good cylinder for every object and a good path object for every fibrant object. And now this is a little bit of technical homotopy theory. The cylinder has the 2 ends going into the cylinder and they're disjoint, and the good path object means that the map from the path space down to the square is a fibration. And now these notions of fibration and the disjoint cofibration inclusion there are coming from model category theory, and that's what the machinery that I'm going to use next to describe this setup. I'm going to put a Quillen model structure on the category of cubical sets. And the Quillen model structure is as follows. The cofibrations, you can just imagine they're just the monomorphisms. In fact, I'm going to axiomatize, but I'm not going to show you the axioms, a class of monos, and so this is kind of parametric in the cofibrations. And that turns out to be useful for various different cases where you can take different notions of cofibration. The fibrations, that's a little bit of a technical looking condition here, but it's really just the usual homotopy lifting property that you may have seen before in homotopy theory. It's a generalization of the path lifting property, but it has a kind of generic endpoint. You lift a path not by saying, take something over one end and then lift the whole path, or take something over the other end and lift the whole path. But the idea is that you can take any point on the path and then take something over that, and then you can lift the whole path. So that's a kind of fancy way of saying that. The weak equivalences are what they have to be, namely the composites of trivial cofibrations and trivial fibrations, but they can also be described independently by this kind of bijectivity under pi0, the bijective on connected components when you post-compose with a mass into a fibrant object. That's a kind of familiar condition. Maybe if you're familiar with Joyal's model structure for quasi-categories, this is the same notion for the weak equivalences. Okay, so I'm going to explain some of the details of this model structure to you now, but what I really want to emphasize is the connection to type theory. That's the interest here, not the model category stuff, because the model category theorists can, spin this thing off in their sleep by looking at what the index category is and what the interval is, and using various different sophisticated methods. And the construction that I'm interested in uses ideas coming from type theory to build this model structure, and that's what I'm going to kind of emphasize here in this talk. The proof of this theorem, like I said, it uses ideas from type theory. It actually makes use of the univalence axiom in a kind of reversal of the original use of the model structure to build a model of univalence. This kind of reverses that in the sense that it implicitly, at least, proves the univalence axiom under this interpretation and then uses it to derive one aspect of the model structure. Maybe it's a little bit like, I'll say a little bit more when I get to it. And the way this works is we axiomatize the construction. There are basically three steps. There's a classifier for the cofibrations. There's the interval, which has this tininess property, which I mentioned. And then there's a universal small map, maybe a little reminiscent of some ideas coming from algebraic set theory, at least for me. It plays a role also in the type theory to have a universe in the sense of Martin-Löf. And these are the basic ingredients which will give rise to the model structure. And then having axiomatized this setup and then giving the proof axiomatically, we can of course apply it in several different cases that I won't have time to mention, but we've made use of that fact that this is kind of parametric in some of the structure. So the actual construction goes in 3 steps. These structures that I mentioned determine in turn one weak factorization system of cofibrations and trivial fibrations using this cofibration classifier. The interval, we throw the interval in, then modify the first weak factorization system to get the second one, which gives us the definition of the fibrations, and then the universe is used in the third step where we show the 3 for 2 property. So I hope that's a little bit familiar to some of you, at least if you were in the A track yesterday, you saw the axioms for model structure, and so maybe this will ring a bell. I'm going to go through these 3 steps, but I'm going to go through them. The first 2 steps are fairly routine. There are some interesting type theoretic ideas in there, but I'll kind of rush through them. And then the third step is where the real action is, and that's where I hope to have a little bit of time left over at the end to tell you more about that. So the first weak factorization system of cofibrations and trivial fibrations is given by this classifying object. You might as well think of this as omega if you're a topos theorist. If not, it's a sub-object of omega. It classifies the cofibrations. And then the trivial fibrations are just the maps with the right lifting property. With respect to those cofibrations, what's important about this class of cofibrations now is that because it's classified, they're stable under pullback, and moreover, they have various descent-like conditions because they are classified. And the classifier itself gives rise to a polynomial endofunctor, like any map in a locally Cartesian closed category. And this particular polynomial endofunctor, it turns out, is a monad, and that follows from the laws that we put on the cofibrations. They're essentially the laws that Tito Mussolini called dominance. And these laws of dominance make this endofunctor, polynomial endofunctor, into a monad. And since we know it's a monad and it's fibered, then the trivial fibrations, turns out, are just the algebras for that monad. And that plays a role later on in a way that I hope to be able to point out to you. The fact that this weak factorization system is not just any old weak factorization system, but it's an algebraic one in the sense of Richard Garner and Emily Real. That algebraic character is related to some ideas coming from type theory that I don't have time to explain in terms of uniformity and type theoretic definability. So the algebraic, and really in Richard Garner's original work on natural weak factorization systems following from Walter and yes, that's right, Marco Grandi's, relate also type theoretic definability ideas to the algebraicity or the naturality of the weak factorization system. So that's popping up here again. So that was the first weak factorization system with its algebraic character. The second one we get by throwing in the interval, and then we use this kind of Joyal-Tierney calculus with the right and left. Use a little notation here for it. The push-out product and the pullback column are related by an adjunction, and that gives us the fibrations as those maps whose pullback palm with the interval are trivial fibrations. Again, this is a kind of lifting property, but here again, because the first weak factorization system was algebraic, this one is also algebraic, and that's going to play a role too in just a minute. And then the trivial cofibrations are what they have to be. They lift against the fibrations. Okay, so now the weak equivalences. We know what the weak equivalences have to be. We have these 2 weak factorization systems, and so we can say, take those maps which factor as a trivial cofibration after a trivial fibration after a trivial cofibration. Call those the weak equivalences. We have the 2 weak factorization systems. Just formally, we assemble that into what Reed Barton has called a pre-model structure. That immediately satisfies a nice kind of compact condition, which makes a convenient stopping point on the way to building a model structure. All we have to do now is show that those weak equivalences, defined in that way, satisfy the 3 for 2 property, and then we're done. So that's a nice way of articulating the construction of the model structure. I guess it comes from Joyal and Tierney's work. So that's our next goal now. We're going to show that these weak equivalences satisfy 3 for 2. And in order to do that, we use the third ingredient in the axiomatization, that is this universal small map. So what I'm going to do is I'm going to build out of that V, which was the universal small map. I'll tell you in a moment where that comes from. I'm going to build a universal vibration. So there will be a universal vibration here, the base of which is a classifying type for vibration structures. So I hope to be able to explain that. Then I make this universal vibration. Every vibration is a pullback of this one. I showed that this one is univalent, so that's where a little type theory comes in. And using that fact, I show that the base of the universal vibration is in fact a fibrant object. And that is the step that I need to get the 3 for 2 property for the equivalency. So that's the sequence of proofs there, which I think is a new kind of approach to building a model structure. Is you build this universal gadget, you prove that it's univalent. Univalence implies that the base is fibrant, and then there's a very formal, the whole thing is quite formal. The base being fibrant implies the 3 for 2 condition on the equivalence. So the whole thing is kind of a neat new approach, I think, to building a model structure. The idea of doing things not exactly like this, but roughly like this, is due to a young category theorist, type theorist, I don't know what, named Christian Zettler. He's the one who had this idea that you can, and I think it goes like this. The Awodey model of univalence in simplicial sets uses the entire model structure. It really uses some very subtle properties of the model structure, the descent property and various other things, in order to establish univalence. And what Zettler recognized was, once you have all that, if you have a model and it has univalence, you can get the model structure back out. And that's kind of what this proof is doing. It's some sort of a, I don't know, maybe it's a kind of completeness theorem in the sense of categorical logic, right? It says you have all the ingredients in a model of univalence, you have all the ingredients that you need to get a equivalent model structure, and moreover, one with a special kind of descent property. It's representing an infinity torus. Comfortable with that point of view. Okay, so how does it go? First, let's build the universal small map. Let's see if I can do this in 5 minutes. The universal small map used to be called the Hoffman-Streicher universe in type theory. It works like this. The category of elements functor you know and love. Whenever you have presheaves on any small category, you take the category of elements and you get a category. That functor has a right adjoint, which you may never have noticed. I'm going to call it the nerve of the, with respect to C. So for any category, A, I can take the C nerve of A and I get a presheaf on C. That right adjoint nerve functor now, let's apply it to sets or small sets, pointed sets, up, projecting down. What happened? Okay. And so this gadget here is the discrete vibration classifier in CAT. When I hit it with the nerve, I get a presheaf on C, and that presheaf now classifies those things whose category of elements are discrete vibrations. Well, that's all that. The category of elements of a map of presheaves is a discrete vibration. And so just by kind of adjoint transposition here and a little bit of reasoning, I see that this gadget here is a universal map, or a universal small map. And so that's my V, and V dot is the nerve of the discrete vibration classifier in CAT. That's step 1. Step 2 is the following. Remember I told you that stuff about the trivial vibration structure and the vibration structure being algebraic. And the fact that it's algebraic, maybe it's type theoretically definable, means that you can classify it. And that's the important. In fact, if I have a map, being the vibration is a property, but having the structure of an algebraic vibration is more than a property, it's a structure. And moreover, it's a structure that can be classified. And the way you classify it is this. For every map, there's classifying type of vibration structures on that map, and the sections of which are in bijection with vibration structures on the map. So even if this thing is not a vibration, there is this type of vibration structures, it just won't have any sections. And for every section, there's a vibration structure on this map. Moreover, that classifier for vibration structures is stable under pullback in the sense that the vibration structures on the pullback are the pullback of the vibration structures. So if this is a pullback, then that thing laying down there is a pullback. So the classifying type of vibration structures is stable under pullback. So that follows from this fact that the vibrations are given in this special algebraic way, and that proof uses the root functor, namely the right adjoint of exponentiation by the interval. This is maybe Bill Levere's insight that the interval is tiny. I don't think this is why Bill thought it was important for the interval to be tiny, but I think it's nice that it's used right there. So right there we use that root in order to get the stability of this type of vibration structures. Now, what if we take the type of vibration structures on the universal map? There it is. Follow U. Now, it's mapping down to V. Pull V dot back along that type. This, I claim, is the universal vibration. So we need to show that it has that it is a vibration and that it's universal. So that it is a vibration is easy because look, its vibration structures are the pullback of the vibration structures on the universal map. Oh, but this is that, and so it's the pullback of this thing against itself. And so, of course, this has a section, namely the diagonal. So this has a section, so this is a vibration. So you see, it's a completely formal construction, just using the fact that the type of vibration structures is stable under pullback. So why is it universal? Well, if you give me any map, it has a classifying map to V. If it's a vibration, its type of vibration structures has a section, which gives me a factorization of this classifying map through the thing that this is a pullback of. But that is my claimed universal vibration. And so here's a classifying map for this thing as a vibration. So if you think about that argument, again, you'll see it's a completely elementary formal argument from just the fact that the type of vibration structures is stable and pullback. Okay, so that's my quick sketch that this thing is a universal vibration. Now I want to show that it's univalent. What does it mean for this to be univalent? Well, it's a classifier for vibrations, but the classifying maps are not in any sense unique, like with the subobject classifier. However, for it to be univalent means that the classifying maps are unique up to homotopy. That's what univalence means. The classifying maps into the classifier are unique up to homotopy. So here's a way of saying it. The type over U of based equivalences is itself a trivial vibration. Okay? A based equivalence is, I pick an object, I look at the equivalences to that object. Well, if you think about what this is saying, because that's a pointed vibration here, that's saying that this is a path space. It's equivalent to the path space. And so this really is the univalence condition. So that's univalence. It's saying that the identity type, or the path space, is equivalent to this type of equivalences. How do I prove that? Well, if you unwind this condition here in terms of the classifying property of U, you get a diagram that looks like this, a prism diagram, which was in Glebowski's original proof of univalence in simplicial sets. It may be familiar to you. It says if I have a vibration, I pull it back, and I have a weak equivalence back here, then it comes from a weak equivalence up here, which extends along the covibration here. So every weak equivalence like this that's based extends. So that's the equivalence extension property. I'm not going to give you a proof of that. That's where actually a lot of the work is. And now, if I have such a univalent universal fibration, so there's the plane there. Awodey proved it, I said, for simplicial sets. Cocon has a type theoretic proof in certain simplicial sets, and the proof in the paper that I'm telling you about is a generalization of that. Now, the universe itself is fibrant in virtue of this. This is another, result with a history. Awodey proved it using minimal vibrations. Schulman has a proof using 3 for 2. We can't use that because we're trying to prove 3 for 2. Cocon has a type theoretic proof, and now we have a general proof of that. In fact, there's a sketch of that proof later in the slide if you're interested. And then finally, we apply the following fact. W will satisfy the 3 for 2 condition, which is what we're trying to show. Just in case we have this vibration extension property, if I have a vibration and a trivial cofibration, then there's a pullback square with a vibration here. So the vibration extends along the trivial cofibration in this sense. So Zeitler shows that if we can prove that, we're done. Well, look, here's my vibration. I want to extend it here. This vibration is classified here by the universal one, by a pullback. I've shown you, or at least told you, that this thing is fibrant. Here's a trivial cofibration, so there's an extension here, right? And now I use that extension, and I take this pullback, just factor it into 2 pullback squares like this, and that's my extension now of this vibration along the trivial cofibration. So the fact that the base of the universal vibration is a fibrant object essentially is this equivalent to this vibration extension property. And that's what gives me the 3 for 2. So there are the references. Thank you very much for your
Thank you very much, Steve. Thank you. We have questions? Yes, Egan?
I have a question about the first. Can you hear me?
Yes,
kind of.
a bit loud.
I have a question about the first slide.
First slide,
Yes.
the very first. That's be patient then. This one?
Well, I knew you were. Well, the definition of B. What's the definition of B? Yeah.
The second slide.
Right. So there is so if you think of the opposite of delta as finite bipointed linear orders,
Yeah.
there's a factor from delta to cubes,
Other way.
right?
Other way.
So what is the relation of the non-structured simplicial sets, and what do these adjoint functors do?
The functor that you're talking about, I think, goes the other way, right? Delta is itself bipointed. Oh, I see. You're talking about the geometric direction. Yes. So there's a functor from simplicial sets to Cartesian cubical sets, which is classifying the underlying bipointed object of delta 1. Is that what you're suggesting?
So I was rather thinking, what is the relation between model structures? Is there a equivalent pair? Can you get all by transfer from
that's people have been all over that, of course, in the last few years.
I don't know, so.
Okay, so this particular model structure is not equivalent to simplicial sets. However, there's a fancier one on the same index category, the same category of cubical sets, where the vibrations have an equivariance condition on the lifting. You know, the cubes have symmetries. The symmetric groups act on the cubes. And if you require that the lifts in the open box filling conditions commute with symmetries, then you get a model structure that is equivalent to the spaces, to simplicial sets. So that's a paper that you'll hear about next year. Work in progress with Emily, who's here somewhere, Thierry Cocon, and the previously named Christian Zeitler and a student, Evan Cavallo.
Thank you.
You're welcome.
Okay, any further question would go at the expense of coffee. So maybe we relegate further questions to the coffee break. And thank Steve.